One of the first peripherals you're going to encounter in this class are general purpose timers. Timers are one of the most important things in embedded systems control. Without an accurate timing, you cannot implement digital control engineering, such as controlling the runtime of an engine, for example. You need to make sure things are latched appropriately at a given period of time. Timers will help you do that. In very large embedded systems, timers are used to just schedule your operating system. While for small applications, we're going to use ISR to deal with this main clock and regular, I would say, pulse on our system. Very large system will use real-time operating system and scheduling that are based on actually a timer. So what are timers? Timers are actually special registers within the microcontroller that are configured as binary counters. So those are registers you can read and write into, but at the same time, they are incremented thanks to a clock, incremented or decremented as a matter of fact, thanks to an external clock resource. Your timers can be preloaded to a starting value. They can possibly have an ending value other than the overflow. And every time your timer overflows or hit the end of the end value that you programmed, you can generate an interrupt. So timers can be as simple as simply counting time, and you just measure where you stand in your clock, for example. So think about it as a second counter, right? You will know where you stand in your in the time in general, or you can configure things to trigger an alarm when you reach a given threshold. Timer register can be used in two different modes. You can use that as timers, so you just count time, or you can also count events. You're not forced to use a clock. You can simply use a signal that will have some sort of positive edge, rising edges, and count this number of edges. So your counter can be used for clocks, also kind of for measuring or counting some external events. Timers are also used as a basis for generating PWMs. Indeed, in PWMs, you are generating a cyclic signal with variable frequencies as well as duty cycles. And you need counters to keep track of those informations. And finally, timers are also sometimes used by external communication function for external communication functions. For example, a UART needs a specific time base in order to work properly, and the timer is going to be used for that purpose. In our STM32 processor, we have up to 11 timers. I'm not going to go through that list exhaustively, but you have plenty of different timers, 16-bit timers, 7-channel, providing you with different functionalities, PWM generation, input capture. You do have resources for IR control. You have a SysTick timer, specific to your DAC. So you really have quite a bunch of different opportunities in order to control time for all your different modules. Let's have a look at what's going on with a simple timer. And we'll consider timer 4 as this example, and I'm just putting here a screenshot from the technical datasheet, and what you can see is the following elements. First of all, everything revolves around a counter. So this counter is going to be incremented or decremented by a clock. And that clock comes from your internal clock, but then you will be able to add additional control like prescalers so that you will be able to modify this time base from the clock to another one and decide if you want to increment or decrement your counter. This counter can be preloaded with a given register, so you can decide of the range of your register. So it will be 32 or 16 bits, but you can decide that you only want to count until 255. So you will actually only use an 8-bit restriction of this counter, and every time you overflow, you will preload it to a given value that will restrict this range. As soon as you get a counter overflow or an autoload register or whatever, you will be able to generate interrupts that will be useful for your processor core to know that something happened with your time. In addition to that, you also do have this additional register that is directly linked to some external signal, this timer 1 channel 1, that is used here to capture and compare. Capture and compare means that you will be able to increment this counter and increment this counter from an external triggered input. And once you have that, you will be able to either count what's going on outside and generate specific interrupts, or also you'll be able to compare with the counter, decide when to stop, generate interrupts, or also at the same time you will be able to create output value and periodic signals. Again, I'm pointing you to these block diagrams because it will contain several interesting information, such as the T11 FP1, the PSC values, that you will be able to use this terminology to search in your technical documentation for these specific keywords and find some more information on how do you set those different values. So as I said, a counter is built around a counter, a 16-bit here, with some auto-reload register. The counter can count up or down, as a matter of fact, and the counter clock can be divided by a prescaler. Those are the common features you will always find in timers. As a result, based on all those elements, the time base unit will include the following three parameters. It will include the length of the counter register. It will consider the prescaler register, so what is the clock frequency you use to increment this counter, and the auto-reload register, from which am I starting from. So the timer's principle will be best explained with this diagram. What is represented here is the value of your counter incremented by every clock values from 0 to a full overflow. And here is time. As you can see, the more we increment our counter, the longer it takes, which makes sense. We need more clock cycles. What happens though is that your counter will keep increasing until you do reach the auto-reload value of your register. So you keep incrementing until you reach this value and boom, you will reload that to 0. So it means that while your counter can achieve the max duration of Tmax, you will in fact reach the value of T desired. Now, your prescaler will play with the slope, how quick or how slow is that going to increment. The size of your counter will play with this axis. Can I go very far up or not? So do I have a very large Tmax value? And the ARR allows you to play with this dimension. So by playing with these three variables, you will need to be able to control any time base. What is a prescaler and how does that work? So the prescaler can divide the counter clock frequency by any factor between 1 and a 16-bit value, as a matter of fact, 65,536. So what you will do, it's controlled by a register, 16-bit register, inside of which you will store the division value that you want to use for your clock. It can be changed on the fly, but takes a little bit of time to stabilize this. This prescaler value, in fact, simply turns on or off a set of flip-flops, a set of registers that will play the role as frequency dividers. Here's an illustration of the timing diagrams when you start playing with the prescaler change. Here's the main clock frequency for your system, and here's the timer clock. As you can see here, the prescaler value is set to 0, which means that no division is performed on our clock. So the timer clock follows exactly the input clock value. After some time, we decided to change this prescaler control register from 0 to 3, meaning that I'm going to divide my clock frequency by 4 in that case, between 0 and 3. And what happens is the following. It does establish, and then I'm starting to get a divided value on my clock frequency. That way you will be able to change your time base once again.